to the video for Lecture 15, Section 4. This video will cover resistance temperature detectors, commonly called RTDs, thermistors, and integrated circuit thermal transducers. We will also talk about some unique measurement issues when using RTDs. The principle that metal resistances depend on temperature was discovered in the same year, 1821, that the thermocouple seatback effect was discovered. Early on, it was suggested that platinum would be a good metal to use. Platinum is good because it has a good temperature coefficient of resistance, and platinum is stable and resists corrosion. So it is a common metal used in RTDs. Copper and nickel are other common metals. Resistance temperature detectors are based on the concept that the resistance of a sensing element will change as temperature changes. The metal sensing element can be either a film or a wire wound around an insulator. The wires and films are thin, so they are very fragile, and they normally are encased in a protective sheath. The sheath provides protection, but it adds mass to the sensor, which will impact the sensor's response time. The metals used are platinum, nickel, and copper, all copper. With these metals, the resistance increases as temperature increases. Over fairly wide temperature ranges, the relation between metal resistance and temperature is nonlinear. The common practice is to use RTDs over a more limited temperature so that the relation used can be assumed to be linear without creating large measurement errors. Here is a linear relation used over a limited temperature range. R of T is the element resistance, and it equals the wire resistance in ohms at 0 degrees Celsius, R of 0 times over 1 plus alpha times the temperature. Alpha is the temperature coefficient of resistance per degree Celsius over the specified temperature range. With RTDs, we need to measure the resistance change, and the resistance change will be very small. Data loggers and interfacing devices normally measure voltages, so we need to use a Wheatstone bridge circuit to convert the small resistance change into a voltage that a PDAC 55 can measure. We will talk more about Wheatstone bridge circuits later. The two figures shows two Wheatstone bridge circuits, and the 3-wire circuit is the preferred circuit. RTD are very good temperature sensors, but they have measurement issues too. One of the issues with an RTD measurement is called self-heating. Self-heating is associated with using a Wheatstone bridge circuit. The Wheatstone bridge supplies the RTD with an excitation voltage, and when the voltage is applied, there is current flow through the RTD. When current flows through a resistance, it generates heat. If the current is generating heat inside a temperature sensor, the generated heat can cause measurement error. To manage self-heating, it is recommended to use an RTD with a large resistance and to use a low excitation voltage. With the large resistance and low excitation voltage, less heat is generated. Two other measurement issues with RTDs are thermal shunting and conduction. The sheathing that protects the RTD element make the sensor larger, which can lead to thermal shunting. The sheathing can also increase heat conduction errors. Finally, RTD sensors elements are not exactly alike. So if you have to replace an RTD, you will need to calibrate the units. You probably should always recalibrate any measurement system when you replace the sensor. Also, note that the type of wiring needs to be consistent between the old and new RTD. So if you have a 2-wire RTD, you have to replace it with a 2-wire RTD. The next type of temperature measuring sensor that we want to discuss are thermistors. They are like RTD in that the resistance changes as a function of temperature. However, thermistors have large resistance changes compared to the small resistance changes that RTDs have. Thermistor temperature coefficients are commonly any order of magnitude, 10 times more than the RTD coefficients. Thermistors are made of silver sulfate or metallic oxides. Thermistor temperature coefficients relationships can be either positive or negative. The metal elements in RTDs were always positive. The initial resistance of thermistors are much higher than the initial resistance of RTDs, so a single-arm Wheatstone bridge circuit can be used to measure the resistance change. Thermistor temperature coefficients are usually higher, nonlinear, so they are usually operated over small temperature ranges. Thermistors are commonly used when you need to measure small temperature differences over short temperature ranges. Low excitation signals are used to avoid self-heating when measuring temperatures. Thermistors can be used to measure airflow and thermal conductivity by using a large excitation signal and monitoring the heat transfer due to airflow or conductivity. Hot wire anemometers usually have thermistors that can be used either to measure temperature or airflow. The last two temperature sensing transducers that we talk about are both integrated circuit thermal transducers. One is the current-based integrated circuit and one is voltage-based. At the current time integrated circuit, thermal transducers have more limited temperature ranges than thermocouples, RTDs, and thermistors, from minus 55 Celsius to 155 degrees Celsius. The big advantage to the integrated circuit thermal transducers is that they have linear outputs proportional to temperature. This makes conversion of the transducer output easier. This slide shows how the current output integrated circuit needs to be wired to be able to measure the voltage change with the PDAC 55. A current output integrated circuit adjusts the current flow as a function of temperature. If the sensitivity is 1 microampere per degree Kelvin, we would expect the sensor to send out 300 microamperes of current when the temperature is 300 degrees Kelvin. As with the RTDs and thermistors, we need to convert the signal into a voltage change that we can measure with a PDAC 55 unit. We do this by adding a known resistance in series with the integrated circuit temperature transducer and measuring the voltage drop across the known resistor. You will do this in the temperature lab. Two big advantages of current output integrated circuit temperature transducers are 1. The linear response, and 2. The current signal does not deteriorate or change with increasing wire length between the sensor and the PDAC 55. Long leads can lead to voltage losses. Current is not lost in the same way. The other integrated circuit temperature transducer that we will mention is a voltage-based device. The voltage output is linearly related to temperature. A common sensitivity is 10 millivolts per degree Celsius. So if the temperature is 20 degrees Celsius, we would expect the voltage output to be 200 millivolts. If you look at the wiring figure, you can see that the voltage output integrated circuit temperature transducers are very easy to connect to a data logger or PDAC 55 unit. Again, let's note that there are other types of temperature sensors. The ones covered give you the basic concepts that you can use to build your understanding of other sensors. This brings to the end of the Lecture 15 Section 4 video and the presentations on temperature sensors. Please write down any questions you have and bring them in class or lab. Thank you.